We want to know to quantify that information to make it amenable to the rehabilitator, to the clinician, in order to have more, to get some help from that recording to see which is the disability affecting that individual. And this is what we can do. From more simple to more complicated, the level of recruitment of new motor units, the rectified average value, the average quadratic value, changes in the conduction velocity or in the frequency of activation of active motor units, the compression or the expression of the spectrum. This can be recorded by means of the average frequency or median frequency, and also the retardation between channels, the delays between different neighboring channels. Microphone, please. For us to clinical applications, we have applications in the CNS, in disorders of the CNS. Also, the peripheral nervous system, we hear very poorly. We can look at obstruction. Now, they have been switched off, both of them. I'm sorry, both. Se han apagado los dos. Que le pase el otro, que le pase el otro. Pásale el otro micro. Sorry about that. Oh, here we are. This sounds better. As I was saying, one of the main interests is to look at the anatomy of the muscles, as mentioned earlier. In the muscles, there are several innervation areas, and one of the possible applications is during labor and delivery. For instance, if you do an episectomy, the doctor may know exactly where the innervation areas are, in order to plan where to make the cut and to prevent any urinary incontinence. Also, during rehabilitation processes of patients who've had some cord lesion or brain lesion, we will know exactly the motor units and the innervation areas. Thus, we can monitor any changes taking place in that individual. Additionally, we can understand better the structure of muscle fibers. We can look at the geometry of the muscle, whether the muscles are in parallel or in series, the attachment with the tendons, how far the muscle goes, and this is all related with the strength that the muscle can create, the force. By way of an example, let me show you this study, which we did on patients with lateral epicondylitis. We looked at the wrist isometry in 3 muscles: the radial muscle, the extensor digitorum, and the extensor carpium lax. As you see, there's a difference between healthy subjects and patients. In healthy individuals, contraction is for the carpus radialis, whilst in patients, the contraction is sustained by the extensor muscle. Differences were also found in the participation of these muscles in the same contraction process, being greater in the healthy individual. In the case of the patients, the MCV was more prominent. This shows up a muscle imbalance, which may be caused by the overuse of muscles in lateral epicondylitis. This disorder causes repetitive contractions, and these repetitive contractions generate a change in the pattern, which ends up with a lesion, which ends up being a tendinous lesion. Additionally, we look at myoelectric fatigue during sustained contraction, expecting the CNS to recruit a greater number of slow twitch fibers. It is expected that the conduction velocity of the fibers will diminish, as well as other variables, which are the frequencies. In this case, we have an isometric contraction of the hand. We draw up the fatigue diagrams looking at the evolution of the classical parameters in time. And we define the indices as the slope, the linear slope of these parameters. In the case of healthy subjects, this significant index for conduction velocity is this, whilst in patients we see different results. And in both populations, we see that the fatigue index is greater in patients than in the healthy. And again, these are patients with lateral epicondylitis, which is usually understood as a tendinous lesion. This is also useful for isokinetic exercises. We use these isokinetic exercises to see the variation of the muscle pattern in different degrees of movement. For instance, we see a greater activation of the flexor muscle and of the extensors during extension, but we can compare the different patterns. Finally, the detection of and classification of motor units is also important in order to understand how the CNS works. So we need to identify within the signal the different motor units which are active. Once you got the active units, you have to classify them in order to know how many there are and what shape do they have. You can look at duration, amplitude, etc. Looking at this one here, for instance, we have 4 classes plus an outlier, a huge outlier. The outliers are superpositions of different potentials, and they are more complicated as the signal becomes more complex. Usually the classification isn't very simple. This slide, for instance, shows 2 simulated signals with 5 motor units and 3 motor units. There is a clear difference in the groups, suggesting that the classification is simpler. But in 5 motor units, the potentials blur or merge together, and it is very complicated to tell them apart, to tease them apart. So it's pretty difficult. When there are very many motor units, the whole thing becomes complicated. So by way of conclusions, we've shown you the mechanisms which generate and control voluntary muscle contractions. We've looked at the different variables in the MG signal and the different pathologies. When we've presented an example of application in patients with lateral epicondylitis, we've seen a difference in the pattern of muscle activation and higher rates of fatigue in these patients. And now we will run a short demo in order to acquire a signal, I believe she says. Microphone, please. We need a microphone for the speaker. I believe he's saying that he's going to use a matrix, a linear matrix. I believe he's saying that he's going to put the linear matrix on the hand to see the potentials. For each visualization window, we've seen only 40 milliseconds. We see how the potentials begin to appear. It's a relatively short period of time. This is 1 second. The signal looks very noisy, but then we can see how the potentials propagate and even the appearance of some innervation area or innervation zone. In this instance, we see that in this area there is a zone of innervation, whilst in this point here there is another one. And we can see that in the course of time there's a shift or a displacement from the point of innervation down to the tendons, which would be at the ends of the muscle. Thank you for your attention.
Muchas gracias por la presentación.
Thank you very much. Very interesting paper. Are there any questions for our speakers? I'd like to ask you one. Is there some sort of practical application with real patients? Well, we've shown you the application of a project with a Gara Mutual. This is a Terrassa health management organization to work on patients with epicondylitis. These are repetitive contractions leading to the problem. To design better exercises for the rehabilitation. And with other hospitals, we are working with a hospital clinic for orthostatic pain, people who, when standing up, they begin to tremble. They tremble a lot. The lower limbs cannot be controlled, so they cannot work in certain places. Or for the Goodman Institute, with incomplete cord section, for gait rehabilitation processes, and others.